Okay, so let's make a start. So good morning and good afternoon or good evening to everyone who's joined us today. Thank you very much for attending. So my name's Andy Williams. I work at the European Southern Observatory, ESO, which is an intergovernmental organization for astronomy. And I represent us at the UN Committee on the Peaceful Uses of Outer Space. And I've been thinking a lot recently about the impacts of satellite constellations. And the panel that we are having here today in this conference is on governance and long-term sustainability in low Earth orbit. So I'm really pleased that we have a set of excellent speakers who will give a short presentation on the subject. And then at the end, we'll have about a half-an-hour discussion where you're more than welcome to ask any questions to the speakers or about this topic in general. And the basic issue is the growth of new space activities and to some extent old space activities has led to an increasing and growing overcrowding in LEO. We've got a huge number of active and defunct objects proliferating in LEO space. And of course, all the new projects offer many interesting benefits to society, but we're going to hear about a number of challenges that we really have to think about. And we're going to talk about how all these activities can be sustainably governed. So I'm going to now introduce the speakers. So our first speaker is Aaron Bowley. Aaron is an associate professor and Canada Research Chair in Planetary Astronomy in the Department of Physics, Faculty of Science at the University of British Columbia. And he's also the co-director of the Outer Space Institute, which is a network of world-leading space experts who are taking a transdisciplinary approach to the problem that I've just mentioned. And I really recommend that you go to the website and check out this institute, the Outer Space Institute. It's very interesting. Our second speaker is Richard Green, who is an astronomer and assistant director for government relations at the University of Arizona. And he recently served as the divisional director for astronomical sciences at the US National Science Foundation. And he currently serves as the co-lead of the Policy Hub for a new center that's been set up by the International Astronomical Union. It's called the Center for the Protection of the Dark and Quiet Sky from Satellite Constellation Interference. And I am actually the co-lead of that Policy Hub with Richard. Our third speaker is Paula Nunes-Tortari, and she is External Relations and Science Policy Research Intern at ESO. So she's working with me, conducting research for ESO and for the IAU Center on space sustainability and the impacts of LEO activities on astronomy. And last but not least is Thomas Horzensky, who is a research fellow at the European Space Policy Institute in Vienna. And he focuses on issues in space safety, security, and sustainability. Thomas currently chairs the Slovak Space Policy Association, NGO, which also serves as a national point of contact for Slovakia in the European Center for Space Law. And so I know that this is this conference is sort of virtually taking place in America, and I think many of the attendees are primarily from America. So if you don't know ESPI, the European Space Policy Institute, I recommend that you go and check this out. So without further ado, let's go on to our first speaker. So Aaron, over to you.
Thank you so much, Andy. One moment, everyone, as I set up the sharing. And so now to confirm, you should see a screen with my slides.
Confirmed. Yep.
Okay, great. So once again, I thank Andy and the conference organizers for convening this panel and for asking me to provide some perspectives on issues regarding the development of space. I also thank my many, many colleagues who tirelessly address challenges in space sustainability. A principal challenge that we face is how to develop space in a way that does not preclude future generations from also developing space. We must also maintain space for peaceful purposes only, and that we avoid escalation of space weapons or set up conditions for security dilemmas. I cannot go into all of these issues, but I do want to highlight some of them with the purposes of emphasizing the cumulative impact problem. I've decided to focus on 9 points and give very general comments instead of focusing on specific instances, and any other speaker might have chosen a different 9. So, point 1, Earth orbital space is a finite resource. Humanity has a tremendous capacity to underestimate our influence on the environment. That condition has led to multiple collective action problems, often discussed under the tragedy of the commons framework. A driving mechanism of this behavior is that we tend to see our individual actions as having inconsequential environmental impact, but fail to realize that everyone else comes to the same conclusion. And so we fill our oceans with plastic, we change the composition of our atmosphere, and we litter space with lethal junk. To this end, I point your attention to the United Nations Guidelines for the Long-Term Sustainability of Outer Space, of which many of you are aware, which makes the important step of recognizing Earth orbit as a finite resource. Every time a satellite is placed on orbit, a resource is consumed, making it unavailable to someone else. Fortunately, this resource is renewable in principle, although it is being consumed at a breakneck pace. And that pace might accelerate still. Between January 2021 and January 2022, over 1.5 million satellites were filed at the ITU in the Advanced Publication Information System. Even if a small fraction of these so-called paper satellites become real, we may very well exceed having 100,000 satellites in orbit. Point 2, cumulative effects are damaging. Licensing requirements do not adequately address, if at all, cumulative impacts, whether it is space traffic, environmental changes, or light pollution. Industry, in many ways, is moving toward a consumer electronic model in space. This is understandable. It facilitates rapid updates of technology, but at the expense of lots of waste. Point number 3. Earth orbit is an environment, and it is connected to Earth's environment. Examples of those connections are through launch and re-entry, on-orbit brightness of infrastructure and debris, monitoring Earth from space, and space-Earth interactions and atmospheric coupling. Point 4. There are casualty risks on Earth associated with space activity, particularly careless activity. If a spacecraft or rocket body does not demise in the atmosphere, then there is a casualty risk to people on the surface and in planes. Standards, but not rules, suggest that the casualty risk for a single satellite or object should be less than 1 in 10,000. But cumulative effects could make the total risk non-negligible. The cumulative effects of uncontrolled abandoned rocket bodies in orbit are particularly concerning. We have growing accounts of rocket debris re-entering from orbit, damaging material on Earth's surface. Estimates already place the cumulative risk to be about 10% chance per decade of someone being killed by re-entering space debris. And this does not account for the possibility of mass casualties such as debris striking a plane in flight. Moreover, the risk is borne disproportionately by states that did not authorize the launch, particularly states in the global south. Space launches export risk to the world. Point 5. Uncontrolled satellites will be disruptive, as well as raising and lowering activities. So using uncontrolled satellites will become riskier with time. Controlled satellites will require growing support, and regular maneuvers could cause service disruptions and lower the life expectancy of a satellite due to excessive fuel use. This image shows a 20-minute window of an orbital conjunction streaming service showing debris, satellite, and satellite debris close approaches. As more infrastructure is placed in orbit, rare ultra-close conjunctions will become common. Also recognize that many satellites spend only a fraction of their time at the target altitude. Thus, satellites can experience substantial traffic even outside of dense orbital shells. The figure shows Starlink 1214, which spent about 1/3 of its life at the intended orbital shell. Point 6. Deorbiting should be done as soon as practicable. The large number of satellites decaying slowly through densely populated orbital shells are problematic. We need to shorten deorbit times. The off-cited 25-year rule for deorbiting is actually an upper bound in the debris mitigation guidelines and is insufficient in today's environment. Point 7. Brightness mitigation should be part of the design phase, including considerations for flares, glints, and potential brightness increases due to deorbiting. By now, most of us are aware of brightness issues from Starlink and their brightness mitigation attempts. A major issue with the Starlink impact on light pollution is that brightness mitigation was not part of the original design, causing the need for post-design mitigation strategies. Variability is a major concern, and this goes for even small satellites should they have designs that can give rise to flaring. Moreover, the brightness impacts are not limited to satellites. Abandoned rocket bodies are bright and variable too. Space object brightness is not just a concern for ground-based astronomy, but also space-based astronomy, as shown in this Hubble Space Telescope image. Flaring of debris, small sats, both will be a problem. There are often conflicting issues that need to be resolved, particularly when thinking about cumulative impacts. One example is the use of a drag sail on a small satellite. The sail would help to rapidly deorbit a satellite, which is good, but it could also make something dim very bright during the deorbit phase. And finally, the cumulative effects of space debris are already expected to be changing the brightness of the night sky, with small debris being the most damaging. We are enclosing the Earth within a dust cloud. Avoiding the generation of debris is not just a space safety issue, but it is a fundamental astronomy and science issue. Point 8. Rocket launches and satellite reentries are poised to change the upper atmosphere. The growing launch of mass into orbit is depositing soot, radicals, and alumina into the upper atmosphere, which have climate impacts and consequences for ozone chemistry. Even water vapor deposited into the dry upper atmosphere affects mesospheric cloud formation, with consequences for ground-based astronomy and potentially global circulation. Reentry is also an issue. For material that ablates upon reentry, the mass just doesn't vanish. We are looking at a future in which satellite reentry mass for some materials, because it's deposited in the upper atmosphere, could exceed that which is deposited by meteoroids by an order of magnitude or more. We do not know what this will do. Then finally, point 9. We must ban destructive ASAT weapon tests. The intentional destruction of on-orbit infrastructure as a demonstration of military capabilities must be avoided. Sudden debris injections in orbit have long-lasting effects and cause major disruptions through increased collision avoidance maneuvers. We must also not accept the fallacy that LEO is already so spoiled that additional debris is of little consequence. Weapon tests, such as direct missiles, do cause substantial changes to the debris environment and make up a significant fraction of long-lasting debris. The plot shows the density of debris as a function of orbital altitude for all debris and also for just ASAT weapon test debris. Two different times are shown to highlight the slow clearing process for atmospheric drag, which is not the same for different altitudes. The energetic destruction of a satellite also causes debris to be placed on a wide range of eccentric orbits. The gray curves here represent snapshots of debris from the Russian 2021 ASAT weapon test crossing much of LEO. Now, in today's context, the thought of an international ban on destructive ASAT weapon tests might seem like an impossible goal, but I remind everyone that Even at the height of the Cold War, adversaries came together to pass the Partial Test Ban Treaty for nuclear weapons, paving the way to the Outer Space Treaty, which prevents the placement of weapons of mass destruction on orbit and has further made any such action an international taboo. So I end this overview with some hope. There is growing recognition of space being a resource, and despite overtly destructive actions by some and other actions that are simply changing the environment faster than what we can understand the implications of those changes, we all want to have access to space. Thank you.
So thank you very much, Aaron. This is very thought-provoking start to this this session. So thank you. So our next speaker, Richard, will delve into more detail in one particular aspect of this. So Richard, I will now share my screen for you.
Thank you.
Okay, is that good?
It is. Good morning and good day, everyone. And we'll plunge right into slides, Andy. So next slide, please. We want to make clear as astronomers that ground-based astronomy is here to stay. So for example, Vera Rubin Observatory, which is going to be a unique telescope that has a wide field of view and takes a movie of the sky to find everything that flashes and moves. There are a next generation of world telescopes that are have 10 times the collecting area of anything now in place, and are much, much, much bigger than the wonderful James Webb Space Telescope, which is a single moderate-sized telescope just put into orbit. These are our tools to address fundamental questions about our understanding of the universe, and for the reasons of expense, for maintenance, for state-of-the-art instruments, such telescopes can never, ever, ever be launched. And so we cannot move astronomy to places above the low Earth orbit that's filling up and changing our view of the sky. So we really require dark and quiet skies and need to find the balance between the next generation of commercial space activity and our continued scientific exploration. Next slide, please. So here's a view of what the sky looks like. It's reminiscent of the picture that Aaron showed you as well. It's a 2-hour time-lapse exposure. At the rate of launches, that's going to be a 10-minute exposure in about 5 years. So our former view of undisturbed natural dark sky is rapidly being changed. Next slide, please. So here's an example. Here's a picture of the Vera Rubin telescope. And it's going to address fundamental problems in astronomy, how much dark matter there is, how galaxies came into being, and it needs to be followed up with extra information that reconstructs the third dimension, which is dispersing the light into a spectrum of colors. And so the lower right shows you an instrument with 5,000 optical fibers, each of which can be positioned onto a faint galaxy on the sky. These are key tools being developed in the US for actual missions of the US Department of Energy and National Science Foundation to explore the evolving structure of the universe. Next slide. What does a satellite streak do? Well, just to give you an idea, the upper is a modern picture, not with that telescope that's going to come online in a couple of years, but with an existing telescope, which shows you, which is aligned along a satellite streak. The galaxies that comprise the gold sample of probing the structure of the universe are about 27th magnitude, if you're an astronomy fan. And if you're not, I'll just say it's 1% of the photons, the light particles that come of the natural sky from a 1 square arc second patch. So they are very faint. And if you put a streak across the image, that's a logarithmic scale. So the peak of that is 1,000 times greater than the sky background against which you are trying to detect a very faint object. And so that needs to be masked out. That information is lost. The noise produced by the satellite alone masks any signal that you would be getting from these very faint objects. And so you lose an area broader than the peak of that streak substantially. And if the satellite streak is brighter yet, you lose a much broader area, either because you saturate your detector or there are sideways stripes that have to do with the detector's electronics. We understand the lost area based on the growth of the number of satellites. Understanding the impact on the science takes millions of supercomputer hours in order to simulate the search for tiny distortions in the shapes of distant galaxies. And so we're working hard to understand what the actual impact's going to be, but it won't be good. Next slide. As Aaron said, if a satellite is out of control, or if it has a very structured surface reflecting sunlight, it isn't just a uniform streak of light, it's a rapidly varying streak of light. And in that case, you get confused with artificial detection of what you thought were faint objects. So there's an astronomical satellite that I worked on back in the day called FUSE. It has a big mylar covering. It's now tumbling because it's well past its lifetime. And there's its light curve, the intensity versus time, showing you how it flickers as it goes by. It's even more challenging if you have those fibers and you get a little glint of sunlight that you didn't expect. It's very hard to tell, but it changes the detection. And so professional observatories might have to have tandem telescopes just to begin to understand what went through the field of view. Next slide. On the one hand, we are grateful to companies like SpaceX that have been working very hard to diminish the reflected sunlight that comes off their satellites. On the other hand, there is a countervailing pressure at the moment. And so this 64 square meter prototype shows the new trend. The telecom companies want to talk directly to your cell phone from space. That means they have to have a huge high-powered antenna that they unfurl. And these are going to be brighter than the brightest stars in the sky. And furthermore, if they are in truly low orbits, there need to be thousands of them in order to provide the kind of bandwidth that people are looking for. And so these are going to be a terrible challenge to astronomy because they will simply blow out any detector that they cross if their path goes through it. Next slide. There is good software in place now so that we can actually predict how many streaks are going to go through a field of view as a function of time. So here's a simulation where the color coding shows you as a function of time of night how many objects you would see. Not surprisingly, most of them are near the horizon, but there, as certain constellations go to higher altitudes above the Earth, they can be visible all night long. So typically, the fraction of the total number of satellites in the constellation that's visible at any one time is about 5%, and they are concentrated toward the horizon. Nevertheless, it is going to be a challenge to observational astronomy. Next slide. Here, for example, is one of the objects that big telescopes and small telescopes in the Southern Hemisphere study intensively, the Milky Way satellite galaxy, the Large Magellanic Cloud. If OneWeb Phase 2, for example, with 6,000 satellites in rather high realization of low Earth orbit are launched, then every 4 minutes that field will have a satellite streak through it. And so can we do the search for variable stars and the star by star measure of color and galaxy assembly with streaks in every image? It's hard to say. Next slide. There is a wide field of view telescope now in service, and they can count the number of streaks. One of the jobs they do is to look for potentially hazardous asteroids that might smash into the Earth. And so you see that the red line is the number of satellites that are launched into low Earth orbit, and the blue histogram underneath it is the number of streaks that they record, and it tracks quite beautifully. So the story is that if there are the tens of thousands planned, not even 100,000, every twilight image from this telescope, which has about a 9 square degree field of view, will have at least 4 streaks in it. How many orbits of potentially hazardous asteroids are lost and how many false detections there are requires some serious research, but the prospects are not particularly good. Next slide. As Aaron mentioned, there is a chance that the whole diffuse glow of the night sky will be brightened artificially by the small particles that are left when a larger body is destroyed or has an accident and gets shattered into shards. And so that has been modeled. It's hard to know. There has to be an extrapolation for the very smallest millimeter and smaller particles, which do most of the scattering. But that being said, there seems to be the histogram there shows the number of particles as a function of their size, and they come in all sizes. And so if there is a runaway catastrophe in Leo, the sky could almost double, the night sky could almost double in its brightness, and it's very possible that it's already 10% brighter than it would naturally be. So that would be an impact on astronomy as well. Next slide. It is not just optical infrared astronomy that's impacted by the misdirected reflection of sunlight. These objects are, by their design, radio emitters, and they have an impact on the radio sky in many ways. The transmissions, of course, are millions of times stronger, and so they could actually blow out a radio receiver on a radio telescope if they were focused straight down. So we are working very hard to negotiate with the operators that they blank over the world's largest radio telescopes. You can see these the tracks of these satellites there. Every satellite above the horizon is visible all the time to these radio telescopes. And so the more misdirected power they have in their side lobes, the more the total background noise compared to the universe's radio emissions are increased. Next slide, please. The radio spectrum is a commercial commodity, so it has been very tightly regulated by international treaty, and there are certain frequencies that are protected because they are the emission paths of molecules at rest or nearly at rest with respect to the Earth. So there are these protected bands, but we'll just note that arrow in the graph shows that the emissions from satellites are approximately 1 million times stronger than the signals that the brightest objects in space are putting out, which is underneath that arrow. So this is a real challenge that actual downlink frequencies will be unusable, and the fact that they have side lobes and slop over, it makes more and more of the spectrum unusable for astronomical observations. From the ground, these frequencies are protected, but from above, they are not. Next slide. So here's an example where an already protected downlink frequency has the risk of being stepped on by an immediately adjacent, the astronomy protected band has the risk of being stepped on by a very tightly adjacent downlink frequency. You notice in the upper right some footprints of the satellites from above make it very challenging to blank because they are so large to cover a big area at one time. And the other concern is that the noise floor at any frequency just goes up as the number of satellites go up. So it gets harder and harder for these faint detections. So, and then the fact that almost all these operators are now teaming with cell phone operators and claiming they can use the ground-based cell frequencies from space is a controversial point on the one hand. And on the other hand, again, those are the radio quiet zones around sensitive radio telescopes are protected from the side, but not from above. And so we will need to work very closely with operators to make sure that they can actually blank over these observatories. Next slide, please. We'll make the slides available. Call your attention to the fact that our community has worked very closely together to lay out these problems in a technical way and make recommendations for how mitigations might be put into place to try to make satellites darker in the optical and quieter in the radio. So I commend them to you. And the next slide. So we are working, we do give SpaceX credit for trying to be an industry leader to make their satellites less visible. If there is any fraction of the build out for which licenses were requested, as Aaron pointed out, no combination of mitigations can avoid the impacts. We're going to see these streaks. And if the trend is for direct cell from space, these are going to be larger, brighter, more powerful satellites. And for example, the Rubin Observatory's mission can lose 8 to 10% of its data just because they are that bright. As a final note of encouragement, operators and governments do respond to public opinion. So we need everyone's help to make the balance between the new era of commercial space and mitigating these truly adverse impacts. Thanks.
Okay, thank you very much, Richard. So I think there's going to be a spike of public awareness of the importance of astronomy actually just in a few days' time when the NASA DART mission hopefully slams into a small asteroid moonlet. And of course, this work could not have been done at all without really extensive ground-based astronomy. So it kind of underlines the importance there of what you were saying. And I'm just trying to get the next presentation. So we're going to move into now a question about the governance of this. Paula will speak on a research project that we've started looking at the extent to which sustainability is included. And sorry, I'm just trying to share my screen here. Okay. So over to you, Paula.
Thank you very much. Thank you, Andrew. And thank you, Aaron and Richard, for the great presentation of the cumulative effects from the LEO activities, not only in astronomy, but also in the space environment. As Andrew said, I would like now to proceed our discussion to talk about the space governance in LEO. And for that, I want to share a few of the results of the research that we are conducting on the assessment of national mechanisms on the long-term sustainability guidelines and the sustainability agenda. So for that, we aimed to raise questions about the feasibility of implementing guidelines without first addressing broader questions in the space governance. Next slide, please. So we propose to talk really quick background about the LEO activities and the new space, proceeding to what a sustainability governance system has to address in order to be effective, our framework, which consists in 7 countries, and the questions that we addressed when looking to their national law and national policies, our main results and conclusions. I'm not going to extend very much here in the background because I believe that Richard and Aaron did a great job already. I just want to mention a few topics. So the new space does not only make old challenges worse, but they also create new challenges such as the LEO allocation and the spectrum management. And nonetheless, the space governance still fails into recognizing the sustainability and fails to update to meet these challenges. Nonetheless, there are a few important milestones, such as the long-term sustainability guidelines mentioned by Aaron and the space debris mitigation guidelines that are still non-binding and voluntarily, and their adoption pretty much is on the hands of the adoption from the national mechanisms of their member states. Next slide, please. So this transition from hard law, meaning the 5 principles and treaties of outer space, to the soft law, meaning the guidelines, did not happen on a vacuum. The process in which the adoption of new guidelines is done or treaties is done by COPUUS is from consensus, meaning that in the past it was much more easier to agree on new treaties because of the number of spacefaring nations, which now is more than 100 members. So this means that everybody has to agree or be absent about it. This is, for example, the long-term sustainability guidelines took 11 years since they were first mentioned on one of the sections from COPUUS. So just to bring a few examples, that is also hard to, we don't see in the near future that a concrete treaty and binding law is going to be created about the sustainability. Nonetheless, to have a sustainability governance system, you have to be able to develop, adjust, and improve to meet the challenges and the uncertainties of environment. This is used for fisheries, this is used for resource management, and I think it's very useful when we consider space, because space is also a very challenging environment, and the uncertainty is also very important with new actors entering, new activities, space tourism, and solar panels in space, and so on. Next slide, please. So our framework consisted in 7 countries. We chose countries that have already some kind of space activities established. So they are Brazil, Canada, China, France, Japan, the UK, and the US. Some of the countries, of course, have a higher space program already, comparing to some of the emerging countries. And we wanted to address several questions on sustainability agenda and also related to the long-term sustainability guidelines. So we constructed these questions. First, we wanted to understand if they have law or policy already in place. How is the license process, and if they are addressing issues concerning the space environmental protection while granting licenses. How is the frequency spectrum management process? If the country has registration practices, national or international, if it mentions anything about open data and information sharing, if it's addressing re-entry risks, as Aaron said, with a lot of pictures of space debris already, this is a very concerning point. If the mechanisms are addressing anything related to the protection of outer space environment or the long-term sustainability, to which extent they are adhering to the international laws, international guidelines, and standards such as the space debris mitigation guidelines, the long-term sustainability guidelines, and the IDC guidelines. And our main question was, are they really addressing the overcrowding in LEO or not? So I'm going to share a few of the results. We're not going to talk so specific on each question. We're just going to talk broadly on the main results, because the results are very, very big. So one of the things we noticed is that the license procedures from each country is very different. It also is very different on the sense of the end-of-life measures. The adoption of the international guidelines and standards is very heterogeneous, meaning that some of the countries have domestic guidelines in place, and some of them explicitly adhere to the IADC or the space debris mitigation guidelines. But it's also noticed that the ones that have already domestic guidelines in place, that these guidelines usually are related to the international guidelines, which is very important. Another point is the environmental protection that some of the countries just address very lightly in articles, and some only mention in policies by their support or that they are working towards the environmental protection. Another point is that we did not find much yet related to the sustainability agenda that's being addressed on the mechanisms. A major conclusion that we got was that well-established spacefarings, meaning that the spacefarings that already have a space program more articulated, they already have more sophisticated mechanisms also related to sustainability, but they're also the major polluters. So even though they do have articulated mechanisms, they are still the most responsible for the proliferation of space debris, and they are still the most responsible for the space activities. It is still hard to measure the adherence of the long-term sustainability guidelines, which is why the new working group 2.0 on the long-term sustainability is going to be very important in this process. They are aiming to understand how the implementation of these guidelines is being done by the countries, and if any new guideline or the revision of old guidelines will be done. This will be through the work of the working group mainly, but this is still going to take at least 5 years according to the work plan. So we do not see an imminent change in the space governance related to sustainability yet. Thank you. The next slide, yes. So our main conclusions then are that we saw that there is a sustainability intent on the regulations, but mostly they are very technical measures, such as the end of life, space debris reduction, and so on. And these national mechanisms and laws, they do not address basic components of a sustainable system, meaning that they are not worrying yet about the capacity of the environment, the decision-making process, and the rules to manage that environment. And none of the mechanisms analyzed are concerned about the internalized costs of the system, meaning the future costs of the protection of the environment. And some of them, on their license procedures, they even benefit satellite constellations, making it easier for satellite operations to launch more satellites, meaning that the costs of having this license are reduced. Also, the number of satellites per license is also reduced, and the time frame to have a response from these licenses is also shorter. A few examples are the Canada and the United States regulations on license. Thank you very much.
Yeah, thank you very much, Paola. Some interesting research there coming on. So the last speaker is Thomas. So Thomas, are you going to share your screen?
Thank you. I will start with it a bit later in my presentation, as I just have a few visual elements that I wanted to present. So thank you for the floor, Andy, first of all, and for the invitation. It's really a pleasure to be here in this audience. The few points that I prepared for today look mostly or address mostly safety and sustainability in space. This is not to diminish the few points which have been mentioned by my previous speakers on the notions of the impact of the large satellite constellations on astronomy or the darkness of the night sky, but basically reflects the few projects, activities that my colleagues and I have been engaged with in the past few years, which we have investigated in depth and which we think have a relevance at this forum. And in principle, what we prepared, what we worked on in the period that basically the last few years of a period which has been really characterized by First and foremost, I would say the deployment of the first large LEO constellations. We quickly realized that that most of the forecasts that we have seen in the past, especially on how the LEO orbital and the operational environment, how this would evolve for space safety and space sustainability, has changed, and not a lot of those forecasts that we have seen or that we have predicted a few years ago have actually materialized. So it's really something that my previous speakers have already mentioned. It's really the truth. So we have a finite resource in the low Earth orbital environment, and we have a resource which is being increasingly used, which basically contributes to the safety and sustainability problems of its own. But at the same time, and this I think has also been voiced during the session previously, is that we see that these activities have a tremendous, so these activities, while having pursuing a significant socioeconomic value in terms of, for instance, provision of universal connectivity across the globe, are in principle interfering with other activities which have a comparable, let's say, socioeconomic value, and trying to find a balance between that. It's definitely not something that I want to solve with my speech. So I wanted to focus my presentation or my speech on the notion of policy, or in principle, I would say everyone can have a different understanding of what world policy means. Generally, I would say we connect it to public policy, but I would keep it a bit broader in a sense of it's an organization, an aggregation of common resources. It can be public or private to meet the desired objective. And then in this context of ensuring safety and sustainability, there can be different tools and different instruments that we can put in place. And there are basically what I prepared are basically 4 messages that I think can stimulate this discussion even further. And the first one that I wanted to emphasize would be that our policies can be better if they better implement what we have already created. And the rationale for that is that I see a lot of discussion being underway in the space community about what are the different new things that we need to create or develop in terms of policies, regulations, laws, diplomacies, technologies. And I'm not saying that this is definitely not the case, but more in the short-term outlook, we can actually already start implementing many of those things many things that have been already created, and especially in the last few years. And in the last few years, I was quite surprised, I have to say, with how, for instance, industrial actors have come up with their own various initiatives aimed at safety and sustainability. And it's something which we have called, it would be a codification of best practices, and we have seen it at the industrial level. But we still see on the public side, like Paula mentioned previous in her presentation, the long-term sustainability guidelines and other public instruments, for instance, at the IADC level, are definitely one of those instruments that we have, and we can already implement that in the practice of public and private actors in a bit more of a better way. The previous presentations, however, and that would be my second point, indicated we have some gaps. And here, I'll put my screen up. I've selected or decided to show one specific thing as I would say an immediate need. There's something that if we look in the short midterm future, what is in terms of space safety and space sustainability one of the crucial elements that we need to address. And in my opinion, it is something that I have called de-risking the shared usage of the LEO environment. And there is a visualization that I kindly borrowed from a US company, LEO Labs, which is quite interestingly showing one of the problems that we have when we try to manage how we utilize our common usage or our coexistence in the in the LEO environment. And it's the problem of space situational awareness, where it could happen that there are objects, debris or functional that we see, but that we do not see with precision. Let's put it like that. And whereas of seeing objects that can be maybe 20 to 20 centimeters large, due to the forces acting on these objects and due to the limits in our observational capabilities to track, catalog, and further predict the orbits of these objects, we are forced to take into consideration much larger areas, several kilometers by several kilometers even, which leads to a lot of false alarms and to which leads perhaps to a much more conjunction warnings than what would be acceptable. And to complement on that, even if we perhaps have a situation, a conjunction warning that seems highly critical, so there is an imminent collision threat between perhaps even two functional objects in space, we have a problem as we still haven't figured out as a humankind at large the mechanisms how we can effectively, sustainably, efficiently in the long term manage those collision warnings, and especially in situations in which two active satellites, two active and maneuverable satellites are concerned. So we have a problem in managing our day-to-day operations in the low Earth orbit. If I look at how the usage of LEO is evolving, especially in the wake of large LEO constellations, highly dynamic maneuverable launchers, and space tax, the increasing use of small satellites, I think this is an immediate need that we collectively as humankind need to address. Another point, and here I'm bringing a few concepts. So another point that I would like to bring up is, I would like to bring up to your consideration some of the concepts which maybe have not yet been developed that significantly, but which we believe should be further developed as they offer actionable and implementable aspects that would benefit how we collectively manage our orbital resources in a sense of more specifically low Earth orbit. And my colleagues in the last few years have specifically worked on the notion of space environment capacity, asking themselves whether we can envisage, not just on a scientific and technical level, but also on policy and regulatory level, whether we can envisage something which would be, and this is in the title of the slide, a threshold-based models for space safety and sustainability. And they basically identified that it's a concept that is worth exploring, but definitely worth exploring at the bottom-up level at first, but which in translating also then into policy and regulatory aspects would face some difficulties. For sure, some challenges definitely, but it's something which would offer a quantifiable, more measurable approach to estimating if we should do something different in our management, in our collective management of LEO. In principle, what the concept is about is basically it's trying to add a quantified, defined capacity of the low Earth orbital environment based on the field capacity and available capacity. And what's also quite interesting is that based on some resources or based on some trends and developments based on the technology and how the technology evolves based on the operational characteristics, it's a concept which can actually, or it's something which is not, I would say, predefined, but it's something, and this is basically the last modification that I'm showing, is basically it can move up, it can move higher. It's something that we believe have not been explored that much, both at the level of, I would say mostly at the level of policy and regulations, because there has been quite significant scientific and technical discussions on these aspects already. And with the, for instance, with this new initiative of space sustainability rating, we see something which, I would say, in a philosophical level, brings something very similar. So it's something that we believe should be further explored and offer some nice advantages how space safety and space sustainability could be improved. And the last point, I'm sure some of you have heard about this concept, this notion of space traffic management. And we might have heard, obviously, we might have seen different understandings, different definitions of the concept. I don't want to really bring my own or our own definition of what space traffic management is and what it is not. But again, in the principal level, at its foundation, it's something which is very natural to what we, again, as a humanity, are doing in management of the sea transportation, management of the radio spectrum usage. So both in terms of resources and in terms of transportation, there are examples how we have been able to set up in mechanisms and instruments that might not be perfect, but could lead to something which a mechanism or an instrument that is collective and that improves first and foremost safety and in principle also the sustainability element. We believe there's a lot of discussion going on STM. We think that it's a very good approach. It's a very good approach by different countries, that the discussions are ongoing and national initiatives are being put in place, because space traffic management is something that it's not necessarily only a legal thing. It's not necessarily a technical thing. It really brings together all actors with different roles that intersect, and they intersect. This is what the visual is showing. They intersect in something which has to work together, and it has to work together in such a way that these are the different tracks, different activities, different lines of action that can only that needs to work together so as to enable the space traffic management to be something that in the long term is effective, is efficient, and it sort of tries to address to the needs of all engaged stakeholders. So that would be all from me. The last thing that I put on there is that you just an invitation for those of you who would like to further explore these concepts that I presented. My colleagues and I at European Space Policy Institute have published specific public level reports on this matter. So if you're interested, I invite you to scan the QR code or visit our website. And with that, I thank you for your attention, and I'm giving floor back to you, Andy.
Thank you very much, Thomas. Great presentation, and there's already some questions that we can launch into based on what you've said. So one of your points was that we should implement what we've already created, and we can rely on industries to some extent to coordinate themselves and codify their best practice. And there's two elements here. There's, industry. This is the space industry, of course, we're talking about. There's the role that they have to manage the environment itself, and the role that they have to manage the negative externalities that result from their activities. So if we now touch on one of those first, and then I'll come back to the environment part. So Richard, you mentioned how the astronomy community has been coordinating with the industry. Is this a sustainable model as the number of companies grow? Are there any challenges with this approach of voluntary industry coordination?
That's a wonderful question. I think that at least the big companies that are ahead of the game, like SpaceX, that's actually already deploying, would very much like a model in which corporate good citizenship alone was adequate to address at least some of the sustainability issues. So, for example, they are working very hard to reduce the reflectivity of their individual satellite units. There are some issues in radio that are in a gray zone, that the ITU that manages the treaty negotiations, or the terms under which the treaty is implemented, hasn't really addressed. How do you create a radio quiet zone from above? How do you regulate the amount of power that's not transmitted in downlink mode, but is in undesired side lobes? There are some technical issues with radio that are not resolved. So there are two issues. Is there an adequate model for voluntary cooperation for the good and responsible actors? And those issues where they're trying to mitigate that kind of impact, the answer could be yes. There are actors that are more limited in their funding or their desire to be good citizens. And for those, it would be great to codify those good intentions and have it as a condition of licensing. And there are issues for which I think even the main actors would say, we're not going to voluntarily do that. If there needs to be, if there's limited carrying capacity in a given orbit, or you wish to comply with the spirit and terms of the Outer Space Treaty that says that all nations should have access to this limited resource, then first come, first serve is a terrible model, and that would need to be regulated, as our colleagues will tell you. And I think in that case, they're looking for regulatory certainty as opposed to a thrash. So would it work? Probably not in the broadest sense. Can some of it work in the short term? We are hopeful that at least some of the astronomy related issues can be addressed. We have to ask, it's probably in their best interest to address some of the orbit rays, and control over lifetime issues are in their best interests as well, I would think. But you know, that's a challenge. So, but my colleagues are well informed on these questions, and you should hear from them.
I mean, to ask Thomas, so that I mean, the first point is the negative externalities on other actors, but then there's the management of the space itself to allow operators to operate in it. So can we rely on companies to voluntarily coordinate and manage the traffic issues in space?
My simple answer would be no. And what I mean with that is, I feel safety and in a more transversal amount of sustainability is a public objective. And I think that by essence creates a role for public actors. However, I would advise against looking at this role to be just through a strict regulation. And what I mean in here, sometimes people like myself who are mostly dealing with public policies and public actors in space, we maybe tend to look at like this is the avenue where the decisions and where the key decisions are being made. And recently, I heard an excellent example from representatives of one of the large satellite constellation companies who explained that if there is a major pressure, if there is a major push for these companies to be more responsible, more sustainable, find the right word for that, it will likely not come from the regulators or public actors in principle, but it will likely come from their investors and insurers. And it was a perspective that personally I have not really considered myself. I have perhaps been biased by the area in which I work and the actors and stakeholders with which I mostly discuss. But what I mean is that, so there is in principle a public objective which is safety and sustainability, but the public actors can rely on a provision of that service explicitly or implicitly by an industrial or a commercial actor. I don't think it's by principle a bad thing.
Okay, thank you. So I think we've got time for maybe two more questions. So Aaron, I mean, you gave a fairly long list of challenges, which cover many dimensions. So how can we govern this? I mean, what's the solution in your view, or the starting point of a solution?
That's a tough question. I mean, there are a couple different components to that. There in one respect is raising the public awareness of what's actually happening in space, because it's still the case that people hear about what's happening, but there is an already existing loss of connection with space because of city light pollution. And so people aren't noticing things like the changing night sky. And so while the changing night sky might be most obviously relevant to, say, astronomers and stargazers, it is actually seeing those changes that then could help people start demanding different types of action as well. So as one example, I was sitting outside with some friends and we were all chatting. I was the only one who was looking up at the sky. I mean, I suppose that's why I'm an astronomer, but I was just staring up at the sky and seeing all the changes that were there. And finally, I just asked them to take a look up and see that all the satellites that I'm seeing too. And we saw during that time a Starlink train go by. We saw the ISS go fly over, and we saw a flare. I'm not even sure what the flare was, but it was brighter than the ISS. That amazed me. And their minds were blown when they saw this. They had heard about these things, but they had not actually seen it. And then I started talking about some of these other connections that are there, such as the casualty risk and so forth that's associated with it, or the possibility of changing the upper atmosphere. And it just wasn't making a connection with them until they started seeing it. So that's kind of one component of it for starting to build and kind of the public perspective of what's happening. Other areas are to look and to show that it is in fact in the best interest of nations to move forward now, to think about how all these changes are happening now, because the cost of a Valdez incident is going to be much greater than getting ahead of it. And so we've seen a couple questions here that are related to the question that you just asked me. Some of those are like, what do we need to happen to really see these changes occur? And we could look at the double hull requirement for shipping, for oil shipping, where there was a lot of industry pushback saying, no, we don't need this, we don't need this, we don't need this. And then the Valdez spilled its oil in Alaska. And then suddenly, almost instantaneously, people came together and demanded that these changes would come into that there needs to be double hulls, that there would be a phase-in system, and a whole bunch of other rules occurred because of that. Some of them nationally first, but it all set precedent for the establishment of conventions. And so the individual steps that nations can take are going to be critically important for setting practice, for eventually establishing customary international law on this. And I actually do think that even in today's environment, broader conventions will be possible, but it will start with individual actions. And we're even seeing some of that with the ASATs that I mentioned. So we saw that the United States, Canada, New Zealand, Japan, and Germany have all made unilateral declarations not to conduct kinetic direct descent missile testing. Now that's unfortunately very specific. It's not as broad as what I certainly would like to see, but nonetheless, those countries are now bound under international law vis-a-vis other states not to conduct those tests. And so this is the establishment of state practice, and this could lead to actually a very important component of behavior in outer space. So, how do we move forward? Certainly we need more people to recognize what's happening. And so that was the first point that I brought. The second one is I do think we need to, accept these various components incrementally, have nations move unilaterally where they can, but always within the context of building toward a multilateral agreement, because it's only within the multilateral context that we'll be able to avoid things like free riding and various disasters. So thank you.
Thanks, Aaron. And I think that is a very fitting last point that should be made for this panel to really wrap up all the points. And I think we are now out of time, and the room is needed for the next session. So I just want to thank you all for these really excellent talks and points. It was a pleasure to hear from you. I think the session is going to be available as a recording afterwards. And yeah, thank you to the participants for listening and the organizers for having us. So thank you very much, Daniel.
Yes, the sessions will be all available in video afterwards. So we'll let everybody know when they are posted. And of course, we encourage people to use the videos for education, teaching. All the videos will be open access. So thank you, everybody. And we hope to see you in the next session, which is our noon keynote. So thank you.
Goodbye.
Thank you.
Thank you.
Thanks.